Alright, let's see how this video works. I think I got all my bugs figured out now. Alright, so we are talking about balancing chemical equations, balancing chemical reactions. I have down here a combustion reaction between CH4, which is methane, plus oxygen is going to end up yielding carbon dioxide and H2O. What this equation is literally saying is that if you take a molecule of methane, which I have right here, right, there's the one carbon in the middle, 4 hydrogens, right, and you make it slam into an oxygen molecule hard enough, you will end up creating a carbon dioxide and a water molecule. Now let's look at this for a second, because something ain't right here, right? We have different numbers of oxygen atoms on each side of our equation, right? Same number of carbons, we got 2 carbons, different numbers of hydrogens, so we've managed to lose 2 hydrogen atoms somewhere, and we have created an extra oxygen molecule or extra oxygen atom out of thin air, right? This guy wasn't here on this side, right? We have 2 oxygen atoms over here, and we've used those 2 oxygen atoms here, and now it's saying we're just creating another oxygen atom out of nowhere. And the opposite problem for hydrogen, right? We have 2 hydrogens vanishing. So what we have to do is we have to use coefficients to balance this equation. And what we're going to end up doing is looking at this, and we're going to count how many atoms are on each side. So let's actually go ahead and do that first. Over here on the left side, I have 1 carbon atom. That's pretty easy. Over here on the left side, I have, in this molecule right here, 4 hydrogens, and there's no hydrogens anywhere else on this side of the equation. And all I have left is this oxygen molecule right here. So I have 2 oxygens on this side. I'm going to divide this in half so that all of my reactants are on the left side and all of my products are on the right side. Okay? All right, on the right side, carbon dioxide. I have a carbon, I have 2 hydrogens, and I have 3 oxygens. So this is kind of a problem. I need to get the same number of each kind of atom on each side. So I'm looking at this and I'm trying to figure out, I'm trying to look and see what can I add more of. Well, obviously, when I get to hydrogens here, I need more hydrogens on this side of the equation. Now I can't just stick 2 more hydrogens over into this side of the equation to balance everything out. All I can do is add more of what I already have in the equation. I could add more methane over here, I can add more oxygens, I can add more carbon dioxides, I can add more waters. So to get more hydrogens, water is the molecule that I need more of. So I'm going to add another water molecule on this side. I'm going to make 2 water molecules. To show that in the equation, I use a coefficient. Right? I put the number 2 there to show that there are now 2 H2Os. That changes my totals of hydrogen and oxygen. Right? So now I have 4 oxygens on this side, and I have 4 hydrogens on this side. So that got my hydrogens in balance, but now I still need to worry about my oxygens. And now looking at this, oxygens just got a lot easier to balance out. Before I had a 2 over here and a 3 over here, and it was looking like, how the heck am I going to do that? I'm going to have to put 3 on one side and 2 on the other to make an LCM, something like that. But now, with 4 oxygens on the right, 4 oxygens on the right, now all I have to do is add another oxygen molecule. Right? So we got 2 right there, and to show that, I now have 2 oxygens on this left side. I put a 2 right there in front of the O2, and that changes only my total of oxygens, and now I have 4 oxygens. Right, so that's how you balance equations. Right, so that shows you how with models of our atoms, right, we have carbon atoms, hydrogen atoms, oxygen atoms, universal color code, by the way. Red's always oxygen, white's always hydrogen, black is always carbon. But when we get good at this, we don't actually need to use the models anymore. We can do this all mathematically in our head. Alright, so can I pause this for a second while I come up with another equation? No, I can't. So let me go ahead and pull up another equation. Let me get these guys out of the way here. I'm going to do one more without any kind of models. So let's see. Let's get this out of here. And let's put this down here, and let's go for this. So let's do one of my favorite reactions that I like to use in class all the time, and that is going to be a single displacement reaction between copper 2 chloride, so CuCl2, plus some solid aluminum, or aluminium, as it's correctly pronounced. So copper 2 chloride, that's going to be in what we call an aqueous solution, so that's going to be dissolved in water. The aluminum is going to be a solid piece of aluminum, and that's going to end up creating AlCl3 plus Cu. So the copper and the aluminum end up switching place in this reaction, which is kind of cool to watch. You start with aluminum, and right before your very eyes, the aluminum turns into copper. So that means the copper ends up getting dissolved into the solution. So we put a little AQ there to show that it's dissolved in solution. And then the copper ends up falling out of the solution as a solid. It replaces the aluminum where it used to be. Alright, so let's count up our atoms on each side here. We've got copper, chlorine, and aluminum on both sides. So we'll do my little dividing line over here. Copper, chlorine, aluminium. Now I want to list them in the same order, so it's really easy for me to keep track of things, so I can compare them side by side when I get the totals. So first I'm counting up the copper, only one copper. I have 2 chlorines, because it's Cl2. I have 1 aluminum. Remember, that's an S that stands for solid. That's not a number right there. So we have 1 aluminum on that side. On the right side, I have 1 copper. I have 3 chlorines, and I have 1 aluminum. So, what do I need to change here? Well, looking at copper and chlorine, this is one of those weird ones where I can't just change one side, right? So I have 2 on this side and 3 on this side. So on this side of the equation, I can only ever have multiples of 2 chlorine. On this side of the equation, I can only ever have multiples of 3 chlorine. So I need the lowest common multiple, which is 6. So to make 6 chlorines on this side, I need to put a 3 in front of copper chloride. To make 6 chlorines on this side, I need to put a 2 in front of AlCl3. So that is going to change a lot of things. So I got to come back over here. I put a coefficient in front of copper chloride. I've got to change copper, and I've got to change chlorine. So now there are 3 coppers and 6 chlorines. Over here, I put a 2 in front of the aluminum chloride. So that means I need to change aluminum, and I need to change chlorine. So chlorine is now 6, aluminum is 2. And then now I need to balance copper. So 3 on this side, 1 over here. But copper is by itself, so that's really easy to balance. I just put a 3 in front of the copper there. So now my coppers match, my chlorines match, and I just need to get my aluminums to match. And to do that, 2 over here, aluminum is by itself. All I gotta do is put a 2 in front of that one. And boom, we gooch.